Saxon Advanced Mathematics, Lesson 11. We have two topics to cover today, my friends. The first one is circles. We're going to go through just some basic geometry review. I want to show you what it looks like in the book. So we're going to just zoom through some terms and reminders about what all this means. I just want to show you in the book, there's a lot of information here. If you would like to review it yourself, it's there, but I'm gonna hit all the high notes of it, okay? We have a circle. A circle can be thought of as all of the points that are equidistant from a center. Pretend that's a perfect picture, because it is not. It is true that every one of these points on the actual edge of the circle is the same distance from the center. And that distance is called the radius, right? Because on a proper circle, no matter where you draw the line from the center to the edge of the circle, it should always be the exact same length. Remember that the perimeter of a circle is technically called a circumference. Perimeter is the same measure on a polygon, a shape with straight sides. When it's a circle, we call it a circumference. And remember, this has a very lovely formula. Oh, pi 2r. Pi r2, however you want to write the factors. I'm going to write that as an uppercase r so you can see it better. Or pi times the diameter. The area of the circle, which obviously takes all of this space into consideration, is pi r squared. Just to remind you of those. A semicircle obviously is half. Just looking for what else is interesting. Okay. If we have two radii forming an angle, we call that a central angle. And this is called the intercepted arc. When we have a central angle, the measure of this angle and the measure of the intercepted arc are the same. Okay, that's with a central angle. Now let's contrast that with what we call an inscribed angle. An inscribed angle does not come out of the center. It's all the way on the opposite side, and it makes what looks to me like a Teenage Mutant Ninja Turtles head in profile, right? Because here's his mask, here's his eye like that, right? His smile's down here, and it would have little ties hanging off here. That's what I always think of when I looked at inscribed angles, okay? So they also have the measure of their angle. And there's also a relationship between the size of the inscribed angle and the intercepted arc. But they're not the same. The inscribed angle equals 1/2 of the intercepted arc. Okay? You can see it in the picture very clearly. This is smaller than that. The other way we can say it is the arc equals 2 times the angle. So just making up some numbers, let's say this is 20 degrees, then this would be 40 degrees, okay? So we can set up some fun algebra problems using that, and we shall. A couple other things. We talked about the radius. The diameter is 2 radii that form a straight line. So the diameter goes from edge to edge through the center. We also have something called a chord. It is a line that goes from edge to edge on the circle, but not through the center. We also have what's called I'm going to put the center in just so you can see that it doesn't go through. A secant is not just a segment, but it's a full line that crosses through the circle, not at the center, and extends on beyond. And then the last one that's the most complicated and kind of the most cool is when we have, there's a radius, a radii. No, a radius. Radii is more than one. Okay, so there's the point where the radius touches. And we have a line that comes by and brushes just one single point on this circle before it moves off. It doesn't cross into the circle. It just touches at that one point, and that's called a tangent. Okay? Cool thing about a tangent is that if you take the point where the line of tangent touches the circle and draw a radius back to the center, that will always form a right angle. Cool, right? Another last bit of terminology is that whenever we have an arc, we can look at it in two ways. Let me just put some points on here. A, B, C. Okay, so we can see this. We usually look and we notice this part of it, right? So that would be BC. That's the symbol we use for mark. We would call that an arc. We would call that the minor arc. This is not terminology we're going to use a lot. But if you measure this way, which is longer, we would call that arc BAC. We'd call that the major arc. All right, one's bigger than the other, as you can see. I think that's everything that I need to tell you. No, there's more. Let me flip. We talked about the inscribed angle, right? The measure of the angle is half of the measure of the intercepted arc, or you can think of it the other way. The arc equals 2 of the angles, all right? So this, you'll want to know. This is all good knowledge, but this we're going to use to build some algebra equations. Here's something else you'll want to know to build some cool equations. Let's say we have a circle with an inscribed quadrilateral. It does not have to be even or perfect. Let me write this out, and you write it too. It's long and wordy. I apologize. Gracie is scratching herself with gusto over there. This is called an inscribed quadrilateral. I'll stop for a second and let you catch up on that, and then I'll explain what this is. Okay, so here we have a quadrilateral, a four-sided object. It's inscribed, written within a circle. Let's name the points just so we can talk about them. The sum of the measures of any pair of, I should have written this word, opposite angles in an inscribed quadrilateral, I didn't write that again, is 180. So that tells us that angle A and angle C, they're not equal to each other, but angle A plus angle C is going to equal 180, and angle B plus angle D will equal 180. Later, we're going to look at some proofs to show you why this is true, but for now, you can just trust me. Look how crooked my lines are. That's just sad, you guys. But I know you were pretending that they're straight, so it's all good. Okay, and then here's another one, vertical angles. Vertical angles in a circle. This one's X, this one's Y, this one's P, and this one's Q. I used color so that you can see that these two are on this line and those two are on that line. We can say that X times Y equals P times Q. So if you multiply the segments of the two lines that create a vertical angle within the circle, they'll be equal to each other. All right, and then here comes the last tidbit. This has to do with tangents. Tangent segments, let me call it that. I'm gonna have to squeeze my picture a little bit. Here's our circle. Here's our center. Here's a point P that is outside the circle. Then we have two tangents. One that touches on the top, and one, oh, it's not perfect. One that touches on the bottom. Pretend it's perfect, okay? Segment M is equal to segment N. They will be equal. And again, there's a proof. We can look at it another time, but you can just trust me that if two tangents come from the same point and touch on the same circle, then those segments are equal to each other. All right, now let's use all of this fabulous knowledge that we just shoved into our brains. It was probably already there, but you shoved it back in. And let's see how we can use that to set up 5 different algebra problems. The first one says find X and Y. And we have quite a complicated picture. And I'm drawing it for you. Remember that drawing the pictures the diagrams is an important part of the problem. It helps you notice what's going on and it gives your brain a chance to process. It is not a waste of time. And just looking at the picture in the book is not the same thing. Remember that John uses the parentheses to show that this whole thing represents the measure of the angle. That's why he uses the parentheses and the degree thing. It looks confusing, but it's really helpful. X plus 10 degrees. John uses this trick of sometimes when it gets crowded, he uses little arrows to show you what the angles are worth. Okay, so we're supposed to find X and Y. Now, I like to take these problems alphabetically Usually that is a good strategy. And you could do it. You can do it in any order you want. But if you're at the beginning and just kind of like, I'm not really sure where to start, go alphabetical. So I'm going to start with x. So I see right here is where my x variable is. It's this angle. And I can see that this is an inscribed angle that goes like that. It intercepts this arc. Okay, and I don't have any information about that arc, so that's kind of a bummer. But then as I look at it, I notice, well, wait a minute. This angle, angle P, intercepts the very same arc, and this is 40 degrees. So if this is 40 degrees, then this arc must be 80 degrees, right? Because the inscribed angle is half of the intercepted arc. So that tells me that x plus 10 must be, I think I copied something wrong. This is 46. Okay, so this is not 80, it is what, 92, right? That says 46. So I don't even need to know that, but I do need to know that this angle and this angle must be the same size because they have the same intercepted arc. It happens to be 92 degrees, but I don't even need that because that's the doubled up number. I can just say x plus 10 equals 46, right? This angle and this angle must be the same because they have the same intercepted arc. And so I get, let's just subtract 10 from both sides. I know you can do that in your head. X equals 36. Notice it is the measure of this angle is not 36 degrees, but x equals 36. And in order to find the measure of this angle, it would be 36 plus 10. There's where I get the actual degree measurement. Remember, this answer is algebraic. This answer is geometric. All right? Cool. So let's try y. Let's see. Y is, I'm going to use my other color. Y is this angle. It goes like that. It intercepts this arc. I see that angle A, I kind of have the lockdown on John's strategy here, right? So this angle and this angle must be the same. So then I can say that y plus 20, this bit equals 30, the other bit.